Got it.
All right. So we will move on to our first speaker, Eleanor Hanna, who will speak to us about insights from the human visual system, lateral inhibition implemented in Python. So Eleanor, I will hand it over to you.
Thanks, Alice. Let me go ahead and share my screen. So let's see. Okay. What do folks see? Did they see a PowerPoint presentation or did they see a background picture of a dog?
We see presenter view for the PowerPoint.
Oh, that's not right. I don't want you to know my secrets.
At the top, if you click the display settings drop down, you can choose swap presenter view. It's at the top of the screen.
The top of the, hold on a second.
In the black bar to the right of show taskbar.
I'm not even sure what you're talking about. That's, again, off to a great start.
It's right on the top of the PowerPoint.
Oh, yeah, it is. It's covered up by the Zoom thing. That's the problem.
There you go.
Hey.
Oh, there you go.
Here we go. All right. Okay. It's about the level of competence you should get used to for the rest of this presentation. So hi, everybody. My name is Eleanor Hanna. I am a data scientist at Veracast, formerly Velasys. Sorry about the incorrect moniker here. And I work on the consumer graph team, pulling insights about our different users together in new and useful ways for our clients. And I came to data science via a PhD in psychology and neuroscience from Duke University back in 2019. And during my graduate study, I became very interested in a lot of paradigms that are really useful in data science, or at least interesting for data science. And I want to talk about one of my favorite things that wasn't really part of my dissertation research, but it was part of something that I had to teach to Duke undergrads frequently. And I think that by looking at this kind of thing, we get a little bit of insight into how biological models have informed artificial neural networks and just computer science in general. And also maybe can give us a chance to kind of experience that sort of like playful spirit that brings us to data science a lot of the time. So I'm gonna start off with an optical illusion. That's how you start off all of your undergraduate psychology courses. So this is called the mock band illusion. This is an illusion that was actually isolated in the 19th century. And when you observe this, it could either look, you might say that it looks like bands of the same color across each band itself, or you might say that it looks like each individual band is kind of doing a gradient. It might look, for instance, like this is a little bit darker than this area right here. I hope people can see my cursor, but basically if you're just looking within a band, it might look like as you go from left to right, it gets a little bit darker. But in reality, that's not the case. It's just one solid color all the way across. And the question is why this is happening. Why is it that there would be some kind of setup in our eye that would make this misfire for us? And the mock band illusion is basically an instance where one of the biological shortcuts that our nervous system takes has gone wrong. And this shortcut is usually very good. And it's a shortcut that has to do with some unfortunate evolutionary inheritances that we got from our ancestors about how the eye works. So when you see something, light passes through the lens of your eye, and then it has to travel through some vitreous humor. This is a jelly-like tissue, just kind of some goopy substance before it finally lands on the back of your eye, where the neural representation of the image begins to take place. And much like when you shine the beam of a flashlight through, say, a swimming pool, if you can envision that, you get some distortion, you get some blurriness. So you might have one kind of image coming through the reflected light in this particular kind of configuration, coming through your lens, through the pupil. And then once it passes through the vitreous humor, you end up with something that's a little bit blurrier. So essentially the main biological problem that we're confronted with is that we lose resolution in images. And this is bad for us. We need to some certain fitness related extent, we need to be able to detect edges for one thing, and we need to be able to get a certain amount of information about our visual environment so that we can form concepts about what things look like and what environments certain figures might emerge in. It's very important for us to be able to correct this mistake for a variety of evolutionary reasons. So the solution that our nervous system has come up with is lateral inhibition. It's a way of dialing up the contrast at boundaries of luminance. So rather than, this is an extremely 2-pixel low resolution retinal image, we get, our visual neurons are set up in such a way that we get lighter. So on the lighter side of this 2-pixel boundary of luminance, we get even lighter at the boundary than the rest of the block, and we get even darker than the rest of the block on the darker side. Essentially, our visual neurons make the contrast dial up. So rather than this, again, you get this. So how does this process work? Basically, you can think of there being 2 phases to this. We start with light coming in and stimulating. So again, passes through the lens and then stimulates the photoreceptors at the back of the eye. That's rods and cones. We're only going to be dealing with rods today. And then there's sort of like, once we just get this raw, blurry information into our eyes, there's the computational level, which is a series of layers of neurons that are basically set up in such a way that they will end up creating that contrast. Just a quick primer on neuronal signaling to kind of make this a little bit clearer and get some background information. Your nervous system is basically made up of a multitude of chain reactions between neurons. Each link in that chain is a neuron. And a neuron can either, it can excite the neuron next to it in the chain, or it can inhibit it. If neuron A has an excitatory relationship with neuron B, then when it fires, it releases excitatory neurotransmitters into the space between them, into the synapse, that will make neuron B more likely to fire, which means that you'll see neuron B firing more rapidly. If neuron A is inhibiting neuron B, then neuron A will fire a neurotransmitter into the synapse that makes neuron B less likely to fire, which means that you'll see neuron B slow down or even stop its firing. And neurons don't only synapse onto one next neuron down the chain. Sometimes a neuron will be firing off neurotransmitters at lots of different neurons downstream. And they could have excitatory relationships with those downstream neurons, inhibitory relationships, or even kind of a mix of both. And that's the most interesting case. That's actually the foundation for lateral inhibition here. If we're a data science crowd, you've probably done a little bit of looking at an artificial neural network in your day. And it's the same basic principle. So here each circle would represent an artificial neuron, and a neuron in layer 1 might have a relationship with multiple neurons in layer 2, some of which could be excitatory and some of which could be inhibitory, and so on. And this is essentially how the nervous system is frequently organized as well, in these layers, basically. So that's kind of like the extremely quick version of 101 NeuroHorse. Let's return now to the problem we're trying to solve with lateral inhibition. So how does this particular configuration of excitatory and inhibitory connections across these layers end up unblurring an image for us? So let's break it down into an extremely abstract example. We've got here cylinders that represent rods. So again, we have the two kinds of photoreceptors. You've probably heard of rods and cones. Cones see color, rods are the ones that see high precision grayscale. They're the ones we're going to be looking at. All they ever care about is how much light is hitting them at once. This is that photoreceptor layer we talked about. They're the first line of defense that just gets the reflected light through the vitreous humor. It's all blurry. It's the first thing that we see. This photoreceptor layer will then talk to a subsequent layer of neurons. It's the retinal ganglion neurons. You don't need to know that specifically. But there are multiple connections between any given rod and, for this very simple example, a couple of different neurons in the subsequent level. And it's sort of the same pattern as we go down to the next layer. So this top layer of neurons, they might each have a couple of different connections to the neurons in the second layer, and so on. And let's say you've got a really simple visual field here. We've got, again, just sort of two different things in your universe. You've got one really dim plane in your visual field, and then to the right of it, you've got a much brighter plane. Thanks to PowerPoint, this looks a little bit faded, but think of this as just being a very bright gray and this being a very shadowed, dark, lack of luminance. So let's try now to represent this abstractly with numbers by saying that that bright square we saw before on the right is 40 units of luminance that are hitting each of these rods on the right, and that dim square is 20 units of luminance that's hitting that dim square on the left. So here comes the lateral inhibition. Any given rod in this particular setup has one excitatory connection with one sort of partner neuron in the next layer. And it really wants to convey, I'm going to be using anthropomorphic terms because I've taught this particular concept maybe 5 times, and it's actually easiest to grok when you are using anthropomorphic terms. So I apologize for kind of the soap opera I'm about to spin out for you. But any given rod has that one kind of excitatory pairing with its one special neuron downstream, where it's going to try to convey exactly the amount of luminance that it saw. So this rod right here, the second from the left, is trying to send 20 units of luminance down to its little partner neuron. The rub about lateral inhibition is that the neighbors to either side of that rod, so lateral to that rod, are going to sneakily be sabotaging its special cell. They're going to be sending inhibitory signal that will then be integrated by this guy. How much inhibitory signal? So there is an inhibition constant. I've arbitrarily decided right now on just 0.25. We'll talk later about how you might tune that or scale that. But for now, we'll say in the retina, there is just one inhibition constant that all of the different rods have. And basically what it does is it's a way to scale the amount that it's being excited by the rod. So we are getting 20, so let's look at this now, third from the left rod. It's getting 20 units of luminance hitting it, which means that when it tries to sabotage its neighbor, we will scale that 20 down by multiplying it by 0.25. And we're going to subtract that from what's being synapsed onto this little green guy. So we are seeing 20 units of excitation, and then from either side, we're seeing 10 units of inhibition, which results in this cell seeing just 10 units of luminance. The same general principle happens for the brighter thing, the brighter square, I should say. We see this second from the right rod is getting 40 units of luminance that it's trying to send to its partner neuron, but then the sabotage from the neighbors, the lateral inhibition, is going to scale their units of luminance down by 0.25 and subtract that from all of the information that's being integrated onto this neuron, which results in 20 units of luminance. So far, we've just seen that lateral inhibition is, or this configuration of connections, is really good at just decreasing the overall amount of luminance. And that is something that happens. But it gets interesting when you have a rod that has a neighbor on with basically different amounts of luminance on either side. So here we've got this third from the left rod has a neighbor on the left that has the same amount of luminance, is being exposed to the same amount of luminance that it is. And it has a neighbor on the right that is being illuminated much more. So it's going to send to its partner neuron 20 units of luminance, or 20 excitation that is related to 20 units of luminance. Its neighbor is going to be sabotaging it just a little by 1/4 of its excitation. But then its other neighbor to the right has been stimulated a lot more. So the 1/4 of its stimulation that it will sabotage this third from the left green guy by is much higher, which means that ultimately, when we've taken into account the excitatory information from its partner rod and the inhibitory sabotage signal from the rods to the neighbor of this main rod, we end up with a much lower luminance. We end up with just 5. And interestingly, when you see a spike when you perform the same calculation on the side that has the higher luminance overall. We see 40 units of excitation coming this way, -10, -5, 25 units. What this essentially causes is a brighter amount. There's basically more luminance at the border on the bright side and less luminance on the border on the dark side. And ultimately, when we perform that calculation across a lot of different parts of the visual field at once, rather than having this kind of like blocky, blurry, low resolution image, we end up with increased contrast. And that's a way that we can try to correct for the problem of having light shine in through the vitreous humor in the eye. So that's the first part. That's kind of like the background that you need for the biological information about lateral inhibition. Does anyone have any questions at this point about how that works, so that we can move on to the notebook? I'm looking in the chat. Cool, yes, thank you, Mike. I'll look into that. Good, okay, so this is telling me the answer I need to know. So do people see, can you post in the chat? I've got my Zoom all screwed up here. Could somebody say if they see a notebook that says 2D puppies and 3D flowers?
Yes.
Yep, that's right.
Great. So this is the next part. This is me trying to take the insight from the biological computational model and apply it to, first of all, to recreate it in Python, and then to see if, again, in kind of that playful interdisciplinary spirit that draws us to data science, try to see if we can use it for an application that is not image processing. So first I want to kind of talk about how we might take this abstraction of a biological model and put it in a Python notebook. So again, basically, this is sort of a replication of what might happen. This is my dog Jones. She's very cute. This is when she was a puppy, when she used to sleep. Now she just barks all the time. So let's say this is kind of the raw light reflection coming before it even hits the vitreous humor. This is the very first signal. Once it's passed through the vitreous humor in my eye and hit the retina at the back of it, it's all blurry. So, oh dear, how can I see my sweet puppy? We correct for this again using lateral inhibition. And the way I implemented it for this particular application was I kind of borrowed from, well, I didn't really borrow. It was more that the image processing world has borrowed from this already, and I selected one of the things that they borrowed. I convolved the matrix of luminances that you could represent the image as with a kernel that would represent lateral inhibition. So basically, when I was showing you before, either the sort of like constant by which you would be inhibiting the neighbors, that's kind of right here, that's the subtracted constant of whatever is at the side of this. We'll talk about how we would kind of select an inhibition constant in a second. But essentially what we would do is we would convolve this lateral inhibition kernel across this image. So right now, let's say that this is kind of similar to the example that I showed in the PowerPoint. This right here would be a sort of a darker block And this right here would be kind of a lighter block where the numbers are representing the amount of brightness, the luminance. So essentially, if we were to perform this action, there's a couple of other little steps we would need to take. I mentioned that a neuron can excite another neuron or inhibit another neuron. When we're looking at lateral inhibition specifically, once we've gotten to the output of that little green cell, that's an excitatory output. So we can't go below 0. So the first step is to convolve this matrix of luminances with this kernel. The second step is to replace all the negative values with 0. And then, as you'll see, basically what that results in is that overall decrease in luminance. This is as the sabotage by the neighboring pixels gets more and more, higher and higher proportion of the original excitation. There's that overall decrease in luminance, but we see this kind of like increase in brightness on the bright side and an increase in darkness on the dark side. But the third step that we're missing here, so we've convolved, we've gotten rid of all the negatives because that doesn't make any sense, and we've replaced them with 0. And now we need to kind of handle this sort of like overall darkness. We need to amplify the signal. Oh, I actually put that later in the notebook, I'm sorry. I want to talk a little bit about how we would select this inhibition constant now. How much should we want the neighboring pixels or neurons to be sort of sabotaging and inhibiting each other? We can pick at least an upper limit of 0.125 for this case. And you might have already figured out why that's the case. I'll show you right now. When I ran I looked at the maximum and minimum luminances of a laterally inhibited version of an image at a higher and higher inhibition constant. And we got to all 0s when we get to 0.125. And the reason behind that is that if you look back at this kernel, there's basically 8 squares adjacent to this middle square that is sort of the origin of the convolution that are all getting this negative information. So 0.125 is 1/8. It's the point at which the dark and light are in the middle block are the same value. If you go higher than 0.125, then essentially you're going to be switching brightness and darkness. You're going to get a photonegative. So just to kind of like show you what that would look like, we would basically have something that looked like this right here at the side, but it would be bright on the inside where the dog is and dark on the little edges. So back to this amplification that I mentioned was part of this. It sort of helps us, first of all, to see the difference. But sorry, I rearranged this notebook at the 11th hour and I'm trying to figure out what I meant to say. Right, so there's an additional step of amplification of the signal to basically brighten it up so that we can see it again. And I essentially, for this demonstration, resorted to the automatic auto-scaling default in Matplotlib, where it scales everything to from 0 to 1. And the reason for that is that we don't actually need to identify the constant by which we would amplify that first signal. We know that in the nervous system, amplification is one of the most common things that layers of neurons do. We know that some other population of neurons is going to have a configuration that takes that laterally inhibited image and then just dials it up for us. And it's not especially important for the downstream parts of the brain that it be the same amount of luminance that came in. What's important is that it is enough of a contrast in information that whatever we are going to send that image representation to in the brain, if we're going to send it to some kind of memory or try to activate some kind of concept or whatever, we just need it to have the code that will activate that memory or that concept or whatever. Essentially, all you need to know is it's not especially important for the result of the lateral inhibition process to be veridical as far as luminance. It doesn't need to be as bright as the outside again. It just needs to be something that the rest of our machinery downstream knows what to do with. So what that means is that we don't need to decide on a scaling constant for this. We can just have Matplotlib scale it up for us so that we can see it and know that there is some arbitrary constant by which, or semi-arbitrary constant by which we amplify the image. All this to say that when you try to pick an inhibition constant, so this is again getting higher and higher on the inhibition constant. In real life, it's getting darker and darker. If we let Matplotlib just scale it up for us, so we can kind of essentially just shine the light a little brighter on the result of our lateral inhibition, we see something a little disappointing. It's an extremely subtle, if maybe even undetectable change until we get to that equalizing point where the dark side and the light side are the same value. And the only thing that is different is the contrast. So it turns out like when you look at the matrices themselves, these numbers are different, but it sure is a subtle difference when we've turned the lights on enough to see what those contrasts even were. But if you remember, if you think back to the slide, it wasn't just one layer of green dots, it was various layers. So there's many different layers at which lateral inhibition takes place. Essentially, we perform it over and over. So what happens if we iterate this lateral inhibition process? It's a little weird looking, but there is a much less subtle change. So basically, this is the blur that we came in with. Let's say this is this first layer of green dots, second layer of green dots. By the time we get to 3 iterations of lateral inhibition, say this is the representation, the neural coding that got passed on to more complex visual areas in the brain, we have something that looks a little bit closer to the original image. We have edges that are a little bit clearer, whereas before this kind of blur might not be readily identifiable as a dog. We see enough of kind of the ear and the eye and the other ear to sort of be able to link this image representation to our existing concepts of dogs. So this means that we've solved the problem presented by the vitreous humor on our eye to a certain extent. We've been able to get around the problem of blurriness, and even though it doesn't look exactly like the original image, we've been able to make it so that the important stuff, the kind of the edges essentially, are there, and we can use that information for a lot of our important day-to-day neural processing. When we want to try to tune these parameters, so again, trying to approach this from a data science perspective, it would be great to try to tune these parameters in kind of an automated way. But the problem is that finding a cost function for how close we get the resulting image to the original picture of non-blurry Jonesy the puppy, it was very hard to find such a cost function. So I tried looking just at the Euclidean distance. It didn't end up mapping on to what looked to this human observer like the closest match. I tried also looking at comparing the different frequency distributions of luminances. Again, it ended up with something that didn't really look like my puppy. So what I ended up doing was preparing a grid that modulated both the inhibition constant, so making it a sharper and sharper inhibition by the neighboring pixels, and also modulating the number of iterations. So that would be the number of times that this lateral inhibition was performed, roughly corresponding to the number of layers of neurons that we had. So when you do this, you can kind of visually inspect it. Some interesting things pop out. We see that when we are both iterating more and sabotaging more, inhibiting more, there's more and more artifact that we get in the image. So I mentioned before that it's not necessarily very important to our downstream neural processes that we get it exactly right. We just need the important stuff. But we start getting some noise as well once we reach past a certain part. So here, if we look at the inhibition constant of 0.123 at 4 iterations, we see just sort of like a patch. We've lost a lot of the important signal within the dog. we're seeing stuff that isn't there in the original image as far as the way the sofa that she's lying on looks. We're seeing this kind of like biased crosshatch pattern that isn't present in the actual picture. It's just kind of a result of the fact probably that it's laid out on this very like square grid. Not exactly sure even what that results from. But basically you can kind of, for this very simple demo, you can look at a grid like this where you've tuned these two parameters, and you can pick some parameters that kind of map to your own human cost function of what seems most closely to match your puppy. These are my favorite parameters. This is using an inhibition constant right below the equalizing constant. So it's inhibiting almost as much as you can get on either side before it starts to switch white for black. And at 3 iterations, we get a pretty decent, there is a little bit of artifact again. So, but we get a pretty decent reconstruction of the original image. So here we've got, this is the original, the middle is the raw image that has just passed through all of the vitreous goop. And this is what our nervous system could reasonably be expected to try to do something with. I want to point out a couple of things that are interesting. So in the top right corner of this, you can see kind of the pattern of the pillow that is behind Jonesy in the original photograph, which is like essentially pretty lost in the blurry image. We get not only, you know, we might be able to use this kind of like general gradient information that hit our retina for something, but if we wanted to do something, suppose it was very important for our evolutionary fitness to know the pattern of the pillow behind the dog. Maybe there's something very interesting to us about this kind of like arc pattern and the kind of detail on it, the ornamentation. The lateral inhibition has kind of restored that a little bit. So essentially that's, I was glad to be able to get pretty close to the original puppy. If we wanted to kind of sum up this part of it, we know that it essentially what you should remember for the test is that lateral inhibition of a distorted blurry image doesn't give us a totally perfect reconstruction, but it gets close enough for government work essentially. And by taking the 3 steps of convolving a matrix of luminances with a kernel, where the matrix of luminances is just the original set of brightnesses that we get per pixel, with the kernel that is all some proportion of 1 below 0.125 negative with a 1 in the center. And then we replace all of the negative values of that convolved matrix with 0. And then we amplify to some extent, which is basically for convenience more than anything else. Then we can reproduce what happens in the visual system and end up with something close to my puppy. So that's kind of the first part. I'm gonna start straying into some less image processing oriented stuff in the latter part. Before I do that, does anyone have any questions that they could maybe post in the chat or say out loud with your voice too, before I move on?
There is one question in the chat now about whether lateral inhibition is similar to unsharp masking.
I'm not specifically familiar with unsharp masking, but I wouldn't be surprised. So there's a lot of, I think I briefly glossed over this. There's a lot of image processing stuff that we do that we've kind of expounded on a lot that involves convolution on a kernel like this. And I remember seeing something extremely close to the lateral inhibition kernel that I came up with here in being labeled as edge detection. So with that, they did the amplification as well as the inhibition in one step. It's like a 3x3 matrix of -1 with an 8 in the middle. So one thing I always like to kind of talk about when it comes to the evolution of the nervous system is that we didn't get it optimal. We got something that was like pretty close, this kernel that doesn't, that we have that I showed above. I'll scroll up just so I'm not just trying to describe an image with my words. This lateral inhibition kernel here, which is what we think our visual neurons are doing, it's not optimal. If we wanted to really do really good edge detection, we would put an 8 here. We'd have the amplification and the inhibition happening in one step. And we have come up with a variety of different other kinds of kernels that will have different effects. They could blur, they could, again, I'll look into unsharp masking, but I imagine that has its own kernel to convolve on. But it's kind of neat to see that that sort of innovation in artificial image processing could be based on something that we might have gleaned from a biological model. Okay. So with that, I am going to move on from puppies to flowers. So I was really interested in the possibility that I love me a good k-means cluster. I think the first thing that I thought was interesting about data science was the idea that you can just shake a bunch of data points out, and based on some features, they would kind of decide what group they belong to once you give them a little bit of guidance. So I thought that it would be really neat to try to apply lateral inhibition to problems that involve putting points in multi-dimensional space. There's a very small amount of work that has been done to investigate this idea before. If you're interested, you can contact me after the meeting and I can send you this notebook for one, but then also I can link you to this one single example that I saw of a study that did this. But essentially, I would like to just kind of see if basically lateral inhibition can be used to make a scatter plot easier to do a cluster on. So I specifically, just for this experiment, I looked at the famous iris data set. It's 99% certain to me that everyone knows what that is, but in the event that you aren't familiar with the iris data set, it is 50 observations of 3 different varieties of iris, the setosa iris, the virginica, and the versicolor. And it also, in this data set, they provide 4 features, of which we will only look at 3 because that's easier to plot. So the length of the sepal, the width of the sepal, and the width of the petal of the iris. And the idea is that this is a really good data set for sort of new data scientists to use because it has a nice division between these different varieties of iris based on these features. So this is just kind of like a quick example of the kind of thing that we would look at. So again, just looking at 3 of these 4 features, when we plot this set of observations in a 3-dimensional space, we can see that they're kind of clustered kind of close together. They're different enough in this 3-dimensional space that it's not too hard to tell them apart, but still they kind of overlap, as you can see. Some of the setosas, well, setosa is pretty good, but especially I want you to bear in mind that versicolor and virginica tend to kind of overlap. They're sort of one really big glob, whereas setosa is very dense and it's a little bit farther apart from these other 2. So let's say that we are botanists from a long time ago, before there had been any sort of assignment of classes on irises. And we were trying to develop a taxonomy of iris varieties ourselves. We could use some kind of unsupervised approach, such as a k-means clustering paradigm, to cluster these 150 unspecified irises into 3 different groups based on their similarity on these features. And when we do that, these are the clusters. Again, so this is unsupervised. There's no direct relationship between, say, cluster 0 and setosa here or anything like that. But essentially, we see, just breaking down by differences in color, that there's a little cluster down here that looks like it's kind of all to itself, that looks like it's probably setosa. And we see, you know, it's not a terrible, it's not a terrible mapping between this middle guy here and versicolor, and this rightmost topmost guy here and virginica. And if we wanted to try to see how well these alternate universe botanists did with their completely data-driven approach to converging on what actual botanists decided when they were creating a taxonomy of irises. We can kind of check this in a backdoor way. We could train a random forest classifier to solely use not to ignore the information about sepal length and sepal width and petal width. Just look at the assignment of any given iris to the cluster that we came up with when we did a k-means clustering algorithm based on these features. So we're getting rid of the numbers themselves about sepals and whatnot. We're just saying that once we have used these sepal data to create 3 clusters, we want to see if being in cluster 0 means you're most likely to be in Setosa. And when we do that, it works really pretty well, especially again for Setosa, which is really easy to predict on these 3 features. Basically what this is telling us is that clusters that we derived from those 3 features are really good at kind of distinguishing Setosa from all of them, but then also distinguishing versicolor from virginica. It's not perfect, but we can see that it's very good. So let's say we wanted it to be even better. We have a problem in this multidimensional space that kind of looks, I've generalized this out to a 3rd dimension, but even just kind of like flattening this to 2 dimensions in your head, this is sort of a similar kind of problem to blurry vision in a way. We've got these overlapping clusters. They're different levels of, this is actually a really beautiful picture of it. There's a big density of Setosa here. It looks, and the way that Matplotlib plots this is it starts it out with kind of like an alpha already, and then you've got overlapping ones. They're a little bit darker because you've overlapped one dim one with another dim one. So essentially what this is representing is like an increase in luminance. So you've got this sort of like brighter set here, and then a little bit dimmer, but brighter over here, and sort of like dimmer overall because it is more spread out in virginica. We've got what amounts to different levels of luminance, or at least you can formulate it in that way. So what if we took advantage of what we know about lateral inhibition to try to dial up the contrast between versicolor and virginica? So when we do that, I'm happy to delve into the way that I accomplish this specifically, but I'm going to go over it at a very high level here. Whereas before we had, basically we had an image matrix right there for us by uploading an image matrix. We had to create an image here. The iris data set just has each row corresponds to one iris. But in theory, for this to work, we would need the entire 3-dimensional space to be mapped. So we would need basically for every combination, every option that we had for sepal length, we would need a point in the matrix. And every option in petal width, we would need another option. So I represented the multidimensional space as a 3D matrix. At each coordinate triad, it was a 0 if there were no irises that had that particular set of features altogether. But if you had, say, 2 irises that had a petal width of A and a sepal length of B and a sepal width of C, then point A, B, C in the matrix would be 2. I unfortunately wrote a different thing than I said. That's if no irises had that particular set of features, then we would say that in that 3-dimensional matrix, the point would be 0. If there were 2 irises with a petal width of D, a sepal width of E, and a sepal length of F, then the point DEF would be weighted at 2, etc. So it basically corresponds to the number of observations that fall into that particular triad of coordinates. So we've got that first thing that corresponds to the image. We've just made it in 3 dimensions here. And we can't use the same exact kernel we used for 2D lateral inhibition because we're in 3D now. So if you remember up at the tippy top, this it only needs to have the same number of dimensions as the input image. And now this is 2D, we need a 3D kernel. So that essentially you can generalize this to a 3x3 kernel of negative C's with, at the very center, you would have the 1 again. So, otherwise the process is essentially the same. We first convolve that 3x3 matrix onto the 3-dimensional scatter plot matrix. And we take all of those negative values that don't make a lot of biological sense and we replace them with 0. I did amplify as well, just to kind of scale it for human interpretability. But as far as like, that doesn't especially matter in terms of what we were doing this for. What matters is the kind of like the distance on the range that we have when we're doing a k-means clustering analysis like this. So essentially what I did was I ran that lateral inhibition in 3D. And what I ended up with is essentially a different luminance for these little points. So whereas before we had a point that was like, each point was a 1 because it represented 1 iris, 1 observation. After we performed the lateral inhibition procedure, we're treating 1 observation as 1 unit of weight. So when we're upweighting or downweighting based on how close an observation is to a border, it's going to count as kind of more of an iris because it's like more luminant. And if it's on the less dense side, on the dimmer side, it's going to count as like less of an iris. So it's essentially a way to weight the different observations before you run the clustering algorithm. So again, as in the image processing part, it is an overall decrease in luminance. So essentially you might say that everything's sort of downweighted a little, but it's all downweighted by the same general amount. And just the points that are bordering have that increased contrast effect that's so nice. Once I had this set of weighted points, I submitted them to a k-means cluster analysis again. And it's again pretty subtle. What I would have liked to see is something that was very nice and clear and divided between the versicolor and the virginica. And we do kind of get that. The question is it any better than when we don't weight the individual observations by anything? So to probe whether or not that was the case, you can take these new cluster labels that you get once you've kind of adjusted the importance of any given observation before you run the k-means cluster analysis. You can take these new cluster labels that take that into account, and then you can train a random forest classifier again, just on those cluster labels, not on the sepal length or the sepal width themselves, just on what the k-means algorithm thought based on the laterally inhibited weighted points. You can see if cluster membership, after you've done all that, does a better job of predicting the original variety of iris. And it's a little better. It's modest, it's not great. You know, so there was nowhere to go but up with Setosa. These are not raw counts, these are percentages. Versicolor is about the same. But we do see that there is less of a chance for virginica to be mistaken for versicolor than there is before we have done the lateral inhibition procedure. We see a much nicer diagonal here. We see slightly higher values for precision in the versicolor. It's a modest change, but I thought it was really cool that this adaptation that was developed over generations of evolution with no real teleological bent, no intentionality to it, just kind of what was the quickest and dirtiest solution to the problem of blurriness at each generation, was able to be applied to this completely different problem and do a slight improvement on it. You know, I didn't spend a ton of time really refining this. I think that there's a potential to tune this up or down if we change the inhibition constant. We could also change the kernel. You know, it's not, as we sort of talked about a little bit earlier, it's, the cool thing is that we could convolve a kernel on a matrix based on the I in the first place. We don't have to keep exactly what evolution handed us. We could change, we could futz with that kernel a little bit. So just returning up to here. Again, this is the biologically, the one that's pretty close to the biological model. If we were to futz with it to make it more efficient than evolution was going to make it, we could change this to an 8. We could, in other kinds of sharpening kernels that I have seen in image processing, the squares at the kind of northwest and northeast, southeast, and southwest points are 0s, and everything else is the same. We can play with it a little bit. But I think it is really cool that even when we're just taking something directly from evolution, we can get a little bit of an increase in performance on this completely unrelated data science problem of just trying to do a better job of distinguishing classes of things in a multi-dimensional space. Basically, if you need a takeaway from this latter half of the presentation, it's, again, this is all very modest and more playful than anything, but I think that it's really worthwhile to kind of like explore the inputs and insights we get from other disciplines when we're trying to find innovative solutions to problems. And of course, it's always important to remember that computer science owes a whole lot to biology. So that's my presentation. I would love it if you got in touch if you had any questions. I've posted my LinkedIn and my email address. Please feel free to get in touch. I can pass you this notebook as well as the original slides. But in the meantime, I would be happy to answer any questions that anybody has.
What can you say about the efficiency of this versus some other unblurring or deblurring algorithms?
I didn't directly explore the different kernels that we would have. And I'm thinking specifically of just convolution by a kernel. And I didn't compare it against any other kinds of algorithms we would look at. I think that it's not likely to be this new hidden silver bullet that we can now use and apply to a lot of our multidimensional cluster detection problems. I think this is more a demonstration of how these kinds of self-organizing properties are, first of all, present in nature, and then second of all, something that we can study nature to find and then adjust ourselves. So what I mean by this is that I don't think lateral inhibition in the visual system is necessarily the most efficient way to do it, because that's not how evolution works. It reaches a local minimum. That's all it needs, a local optimum. And it doesn't need to find the most efficient way to do things. But I do think that by looking at things like this, we can potentially discover other kinds of, maybe not perfect, but interesting solutions that biology has come up with, and then we can adjust them ourselves. So it's a long walk for me to take to say it's probably not the most efficient way to do it, but it's cool. Somebody asked in the chat if the k-means clustering algorithm converges in fewer iterations when the convolution is applied. I didn't actually look at that. I would bet that it does. That's what I'd want to be true. That would be related to the motivation for trying this in the first place, is that it would make it more obvious to a clustering algorithm what the best centroid would be. But I don't know. I would have to look. Good question.
I have a biology question. What is the vitreous humor good for? It mostly seems to just make it hard to see things.
It sure does. So it was passed on to me in my education as something we inherited from when vertebrates were marine animals. It's something to do with the way it's adaptation to vision underwater that when we came out onto land, we didn't bother to get rid of. We just made this, you know, not terribly efficient shortcut solution to Band-Aid over.
Got it.
So a brief comment. I think when you look at the convolutional neural nets that are used very frequently now, you'll find a lot of inspiration that was taken from the visual cortex. And there might be some neat extensions from the work you've done here into that direction.
Yeah, I think you're definitely right. I've always thought neural networks were cool. They have never been something that I tried to find a home for them in my dissertation, and I've tried to kind of insert them into business cases at Velasys, and it's always been like the wrong tool for the particular application. But I'm a neuroscientist by training, so I think they're the coolest. And as I understand, a lot of there are these convolutional layers that I think draw a lot of inspiration, as you said, from things in the visual nervous system. And I wouldn't be surprised if there were kernels that looked quite like this when we're trying to increase contrast in an image. Cappy just pointed out, vitreous humor helps maintain the shape of the eyeball. That's a good point. But you wonder why we couldn't find some other kind of fibrous way to do that was transparent. You know, it's one of those things, again, where every time evolution doesn't come up with the best answer to a problem, it comes up with a local optimum. I think that seems to be all of the questions, but please do feel free to get in touch if you would like the notebook or to ask some more questions later.
Cool. Thank you very much, Eleanor. This was great.
Thanks, Alice. I had a lot of fun.
Cool. Awesome. All right. So we will go to our, oh, I forgot. When I don't share everything, I can't change the slide. Give me 1 second. I discovered this in a very sad way one day. All right, so we will move to our next speaker now, Clair Thompson, and we'll learn about Prefect as a data engineering project workflow tool. So I will hand it over to you, Clair.
Awesome.
And Clair, just an interim reminder that we are recording this.
Gotcha.
Okay.
Cool. All right. Let me go ahead and do a screen share. You can see the messy contents of my brain. Okay. And there we go. Okay, so I want to start by thanking the organizers for getting this set up. Thank you all for attending virtually. My name is Clair Thompson. I'm a data engineer in the Office of Information Technology at Duke. I work on the data analytics team within OIT. We do, well, it's potentially not the best name anymore. We used to do lots and lots of data analytics. We were slowly making a move into more engineering focused work. And then the pandemic hit, and that's all we cared about. So we're doing a lot of data engineering right now. Before I started at Duke, and I started in September of 2019, I was working as a software engineer and data scientist at a local ad tech startup. And then prior to that, I was a data scientist with Overstock.com. So all of that being said, I want to think about Prefect as a data engineering workflow tool. And the thing that I want to start with is telling you why we landed on this tool to help us manage all of our workflows. So why did we end up here? The answer comes down to finding a tool that fits our team. And so I want to start with just a bit of information about our team to help you understand where we are and what we were looking for. So the analytics team in OIT is a pretty long established team, but we, in the last few years, have seen an influx of new members. Like I said, I've only been on the team for a year and a half. My boss has been around for about 2 years. So in addition to us, a lot of other new team members. And with the onset of the pandemic, as I mentioned, we really saw the focus of our work drastically shift. We were doing lots of analytics, and suddenly we needed to switch and think about data engineering almost full time. So with that being said, we needed a good workflow management tool that could help us manage all of the new jobs that we have running. We had a legacy tool in place. It was not suiting our needs. And it was very clear to my boss and myself that we needed to find something modern, something that could handle our very diverse needs. And we wanted to find a tool that would not only manage the data engineering needs, but would also be something that was suitable for a variety of people with lots of different backgrounds, all the way from heavy analytics work to people like myself who spent time in ad tech. So we started this process by thinking about some requirements. And I think really the very most important one for us was that jobs be code. So as I mentioned before, we had this legacy workflow management tool where when you create a job, you create it by building out in a user interface, sort of this drag and drop system. And that's fine, but the background, what's living behind the UI is XML. And you can version control that. Good luck figuring out what the changes mean. This became a huge headache for my boss. I saw him get very upset on a number of occasions about not understanding how an original job changed to become a new job, especially when errors were cropping up in these jobs as they changed. So it became very important to us that we specifically be able to manage and track our job changes with Git in a way that made sense. So second, as I mentioned, we have a variety of skills on our team, and we wanted some tool that was fairly easy to learn, so that would not be presenting a lot of overhead for everybody. We specifically wanted something in a language that everyone speaks, so to say. And of course, you know, we're doing lots of data analytics, so Python was what that language needed to be. And then straightforward management was also a big, a fairly important thing for me. This project became my baby. And so I'm the one who's managing the tool. And I knew that it needed to be something that was going to be fairly straightforward to keep updated, not too difficult to install and get running. As you will probably realize very distinctly throughout the course of this talk, I am a data engineer. I'm not an architect. I'm not a systems engineer. So it needed to be something that was pretty straightforward. And then obviously we wanted to handle our modern data engineering needs. We are moving lots of data among a variety of resources, cloud resources, many Duke local resources. And then I gave bonus points to tools that were still under active development. That turned out to be something that was very helpful in the future, and I'll mention more about that momentarily. So we started looking at some contenders. One of the first things that we considered and almost immediately threw out was Azure Logic Apps. We in OIT are using Azure, and the Microsoft folks suggested that we look at this tool, and we did look at it, and it turns out that you manage jobs through a UI. Again, there's no code that you can version control and track changes and know why jobs broke. I'm sure there are ways to do it that are nice, but we specifically wanted code and Git. We also looked at NumFOCUS and ran into similar problems. We wanted to be able to write jobs in Python, and so NumFOCUS wasn't going to work for us. When I started the process of looking for the tool that we were going to land on, I honestly thought, I'm going to look at some things, but we're going to use Airflow. I have previous experience with Airflow. I know that tons of companies use it. And so I honestly thought that was where we were going to land. But I wanted to take some time to look for other options, see what was the latest, greatest. And as I was doing some research, I did run across Prefect. And I thought it was pretty intriguing. It aligned with Airflow and having a lot of or in at least checking off a lot of the boxes that we wanted, just on an initial overview. And so we decided to give it a spin and see what we thought. So in the contest between Airflow and Prefect, there, as I mentioned, are a number of shared positives. They're both open source projects. Prefect was recently open sourced, I think, in the first or second quarter of last year, if I remember correctly. You write jobs in Python, so again, very important box for us to check. They both have web UIs that are pretty nice. And I do want to pause here for just a moment and emphasize that there's a difference between a nice web UI and creating jobs in a UI. It's really nice to have a good UI for managing your jobs so that you can take a look at logs for a job that ran 3 days ago and failed, or so that you can get an overview of how long jobs are taking to run, perhaps see if one is running a lot longer than it used to, track historical changes. Again, the thing that we didn't want in a UI was being forced to use it to actually create the jobs. So we want a nice UI for understanding statistics about the jobs, not for creating them. As a very mathy person, I like being able to represent my jobs as directed acyclic graphs. So that's something that both Airflow and Prefect offered. And then, of course, Airflow had some obvious pros, as I mentioned. I've used it before in a previous position, and it is in my opinion, the industry standard, a very well-established solution. So then I started looking at Prefect. I installed it, started messing around with it, and I found that there were a lot of things that I really liked about it. So the sort of silly one is that it is very shiny. It looks really snazzy. Every time I've upgraded to the latest version, it looks even a little bit shinier, and that's pretty nice. Obviously, that's not the reason that we chose it, but it was a nice feature. It looks very 2021. And then, as we wanted, it is built specifically with modern data engineering needs in mind, which you can see as you look through the docs on docs.prefect.io. If you'd like to read more about this, there's a nice blog post on the Prefect blog that talks about the design decisions that were made in building Prefect and how those differ from those for Airflow. It is under active development. And I'm going to jump ahead. You already know that I've been using Prefect for a while, so I'll tell you why that has turned out to be really awesome. There have been a number of occasions where I just ran into something that made me want to stab myself in the face with a spoon. There was just something that was not working, and I couldn't figure it out. And I went to, on each of these occasions, every occasion that this has happened, I've gone onto the Prefect Slack channel, asked questions, gotten answers from the developers of Prefect within, I'd say, never more than an hour. And every single time they've solved my problem, or at least gotten me to a point where I knew how to solve the problem. So that has been phenomenal. And then thinking about modern data engineering needs, the Prefect API offers a variety of tasks that are specifically designed to be integrated with common resources, many resources that we use here at Duke, such as Azure. So then another really nice thing about Prefect is extensibility, opportunity for customization. If you'd like to make some changes to the build, just alter the Docker files. I have not had to do this yet, but I got really close on one occasion. So it's nice to know that you can do that if you need to. And then I think the thing to me and to my boss that was perhaps the most important in making the final call was the API. So, I spent a fair amount of time in the API and I really liked it. I thought it was really clean, very simple and powerful. And again, they're constantly adding new features to the API. There's both a functional and imperative API, which I like. I tend to try to write more functional code, and lots and lots of conveniences, which I will talk about later when I discuss the API. And honestly, I thought in comparison with the API for Airflow that it was more straightforward, much easier to learn than the Airflow DAG definition. And so putting all this together, we did end up deciding to go with Airflow, it's the opposite of what I've just been saying this whole time, to go with Prefect as our workflow management tool. So I noticed that I had a question here. This is a good place to maybe stop and take a look at that question. Which Prefect license did you choose? The one where there's not a pay for thing. And I will say more about that later. But remind me if I don't. I probably will. Okay. So with all that being said, I want to spend some time talking about the backend and the UI. Then we'll switch and talk about the API in a few minutes. So the back-end architecture is lots of Docker containers. There's a container that runs the engine, the Prefect engine that is, keeps the server up and running. You get a Prefect agent. The agent is the little guy that's going to run around and look for jobs and kick them off, keep a track of them. You get GraphQL, which allows you to query the API, as well as Postgres for managing your job history. And then in terms of deployment, this is where I'm going to talk more about your question. In terms of deployment, there are a lot of options. So if you just want to put this on a local machine, you can do that, and it's free. You don't have to, it's not pay to play in this case. In fact, most of the options I'm going to mention here are free. If you happen to have yourself a nice Dask cluster hanging around, you can install it there. If you'd like to install it on your cloud resources, there are some good options available. There is built-in functionality for deploying in AWS Fargate. Obviously, you can just deploy on an ECS instance if you'd like, more like the local single machine deploy. Azure ML support is coming soon, and I'm pretty excited about that, as again, we are an Azure shop, and this might, in some point in the future, be an interesting way for us to deploy. The only paid version of Prefect is the Prefect Cloud Managed Service. So this is managed by Prefect.io. The nice thing about this is that while it is pay to play for most instances, if you are a single developer and you just want a chance to mess with Prefect and learn a bit without actually having to install it and manage the server, then you can actually use this for free. So that's a great way to just get your feet wet if you're interested in learning a bit about it. You can also deploy it with Dask on Kubernetes if you want to do that. There are lots of deployment options. At the end of the talk, I'll show you a bit of the architecture that we have. For our needs, it has suited us well to do essentially a single machine deploy on a virtual machine in Azure. And so again, totally free. And I'll show you some more about that architecture later in the talk. So that's some of the back end for Prefect. Now let's look at the shiny part, the user interface. Voila. So this is our production sort of front page. There's lots and lots of good information here. The front page gives you an overview of everything that's going on in Prefect. So one thing that's interesting that you can see right now is that there is a job that is currently running. You can look down here to see how long it's been running, which job this is. In terms of all of the visuals you see here, the top bar gives us information, just sort of summary information about all of the most recent runs. So I can see that, about 2 hours ago, we had this job kick off and last run for about 6 minutes, 51 seconds, and it succeeded. Again, more summary information about all of the jobs that have run in the last day, information about failed flows if you have any, as well as scheduled runs that are coming up. So I'm going to click on the flows button up here, and this will take us to a summary page for all of the jobs that we have installed in Prefect. So this now gives us a breakdown sort of job by job for what we have going on in Prefect. For each of these jobs, you can see whether or not there's a schedule turned on. You can toggle that if you want to, turn it on and off. You can see the project it's living in, the code version that you've got, when that latest version was created, and you can also see run history for the job, so the most recent runs of this particular job. Since this guy has a failure, I'm going to go ahead and click into this flow or this job to take a look at what's been going on here. So this particular job, again, the front page for the job looks sort of similar to the initial front page. You've got summary information for the jobs that have run recently, some information that's a bit more detailed about this particular job, as well as scheduled runs. In addition to all of that, I can take a look at the tasks that make up this job. We'll say more about that in a few minutes. Recent runs of the job, as well as the directed acyclic graph for the job. And so I can take a look and make sure that my logic makes sense for building out this particular job. I can see the latest versions and again, summary information. So I'm just drilling down farther and farther into information about this job. And I can, if I want, kick off a run by hitting the run button or just the quick run button up here. So one of the things that I mentioned earlier that I really like about Prefect was all of the nice conveniences that it gives you. And one of those is really clean, nice built-in logging. So I'm going to hit this job that we see has failed and drill down to the particular part of the job that caused the issue. And I can go into the logs and take a look at what happened and see that it looked like it was some sort of bizarre database error that I don't understand right now, but that's okay because it cleared itself up. Anyway, we found this really helpful. The logs are really clean, very well presented. So it's just like, it's easy to dig through and find out what went wrong. All right. So that's the UI, quick overview. In a few minutes, I'm going to actually kick off a job and let you see what it looks like when it's running in the UI, but I'll need to switch to my, I'm on the production server and I want to switch to the develop one before we do that, because that's where my demo job is. So the next thing that we're going to do is discuss the API, which, as I mentioned earlier, I really like. So the core concepts for creating a Prefect job, I like to start by thinking about tasks. A task is just the basic unit of a job. You can think of this as maybe just a definition in Python, maybe a method in a class. The flow itself, that's more like the actual job. It's really just a way to define dependencies among the various tasks in your job. And that's a really important concept to keep track of. I'll come back to that momentarily. Every flow and task has a state. So that's just the current status.
See, this is how much cheaper.
And that can be things like canceled.
Sorry, I think somebody might not be on mute.
Yeah. That can be things like pending, canceled, running, etc.
Gene, do you use powers to help someone mute?
哦，我刚才就说了，本来这个国家是有总统，然后有 Republic 和 Democrat， 就是来互相来制衡。比方说
I'm just gonna pause here.
没有啥事，不能光你一个人说了算，得要大家都。啊，结果现在他搞的都是民主党，那以后他们说个啥，他们就是这样。他想定什么就是定。
Pretty much, Biden gets whatever he wants.
Yeah， 就没有一个监，没有一个猫，
And
there we go. Good job, team. Okay, so states is just the current status of a flow or a task run. And then state handlers are little bits of code that we use to respond to a changing state of a flow or task run. As I mentioned earlier, we also get really nice built-in capabilities for logging. There's also, as one would want, good scheduling mechanisms and nice ways to add parameters to your jobs or flows. So this is sort of the core concepts. There is much more functionality than what I've listed here. Quite a lot of very rich functionality. I'm only going to be discussing more of the basics here, but know that there's a lot more out there and it's pretty cool. So the thing that I want to think about for just a moment is the idea of defining dependencies among your tasks. It's a really important thing to do when you are creating a job. So in Prefect, there are two ways to do this. You can do it implicitly. So let's say that I've got two tasks and task number 2 takes the output of task number 1 as a parameter. Well, if that's the case, then you don't explicitly need to say task 2 should wait on task 1. Prefect knows that that is the case. And so that's just an implicit way to define a dependency. But of course, there are many times when you aren't going to be implicitly defining dependencies, but you still want task 2 to wait on task 1 to complete before it runs. And in that case, well, there is functionality in Prefect to just explicitly set task 1 as an upstream task for 2. And you'll see this little bit of code later in the talk to do that. So this is sort of the explicit way to define these dependencies. So when you're writing a flow, maybe your first time, you've never done this before, maybe sort of the heuristic way to think about doing this would be to start by just writing a Python script. Just write whatever Python you want. And then take your definitions and decorate them with the task wrapper that Prefect provides for you. So once you've decorated a definition with @task, Prefect will know that that is a task it needs to register and keep track of. And then you'll write your flow definition. So you're essentially like defining the dependencies among all of these tasks. One thing to note is that tasks can run concurrently. So you do need to get your dependencies correct. Then, oh, that's it. So that's pretty much all you have to do. And so to think about doing this, I'm going to give you a very simple toy example, very boring example, but we'll look at a more interesting one in a moment. So I've got a very silly little script here. It has a definition to generate a random number, and then if you run the script, you'll get your favorite random number, presumably. So it's really easy to take this script and turn it into a flow. So first, you'll need to obviously import the correct Prefect classes, and then take your definition and just give it that wrapper. The last thing that you need to do is write your flow definition, which in this case is really boring. There are not any dependencies, but that's okay. Again, we're going to look at something more interesting in a few minutes. So as I mentioned earlier, I liked the API a lot because it felt like writing normal Python. You can see that for the most part, like these scripts pretty much look the same. There's just a little extra functionality. There's a little extra going on in the Prefect version. If you wanted to take this Prefect script and actually get it on your server, you would add one little extra line of code. So you would add a line that says flow.register. So that tells Prefect to take this definition and register it with the server. And now if you run the script on the right-hand side of your screen, you actually will get the flow up in the Prefect UI and you'd be able to use it. I saw that I have a couple of questions, so I'm going to stop and answer those. Type of static checker that will validate your Prefect flow code. I think that there might be, but that is definitely something I've not delved into. So apologies, I am not entirely certain about that one. Yeah, I can't answer that question.
Is that my question about the static checker?
Yes, yes.
Okay. In the code snippet that you're showing on the current slide, is flow.register within the with flow context?
No.
Or is that it is not?
So it's
so does it looks like lowercase flow with the in the with statement would no longer exist after you outdented to the left.
Well, it does.
Okay.
You're right. Now that I think about it, I'm not a Python person per se, so I hadn't thought about that, but somehow it magically works. This is actually how it's done in the Prefect documentation as well. So.
Okay.
So I guess it just lives around there. But you're right. I guess maybe that's less Pythonic, but it works now. Anywho, good point.
Okay.
I'm going to move on to a demo, and that means I'm going to take just a moment to switch the server context here. Let's see. So again, I'm just switching over to my dev server. All right, cool, that looks good. So let me share screen again. Okay, so we're going to dive into a flow in a little more detail. So this is my dev server. Everything's broken per usual. So the flow I want to look at is Prefect demo. And I'm going to show you what the flow looks like here. So I've got a final task to send an email, and that has to wait. So it has dependencies. It has to wait until this task to get local data runs, as well as the task to get Azure data. Get Azure data has to wait on these guys to run. So the get creds task will have to run first. I'm going to just kick off a run so you can see what this looks like. It's kind of cool. The timeline is flashy. That's a new feature, but you can see that all of these tasks are running, and you can get this comparison of how long each part of the task takes to run. So I want to think about the code that goes into building this flow. So again, I have a task that's going to get some text from a local file, and a task to get some credentials from Azure, or for Azure, that is. And then one to read some data from our blob storage in an Azure account. And all three of these tasks were actually just basic plain old Python functions that we just decorated. So these you would just write as you would your normal Python code. And similarly with the last task, which is to send an email. So I'm going to show you not what the particular details of those definitions are, but how we would stack these things together to get the flow that you saw a moment ago. So we have our opening statement that defines the flow. One thing I'll point out that I'm going to come back to later is information about scheduling and adding state handlers. Just as a sneak peek, you can add those into the top level of the flow as parameters, and then you'll get a schedule picked up. You'll get the state handlers. So we are going to run these separate tasks. So the get credentials task, which will then parse out to different parts of the credentials. We had that task to get some local data, and another task to get data from Azure. Notice that this particular task had to wait on a previous task to run because components from that or output of the task to get credentials are parameters here. So that's an example of the implicit definition of dependencies. The final task here is to send an email, which actually sounds like it just showed up in my inbox. Email server's a little slow. And you will see here that I needed to set an explicit upstream task because this output of the Azure data function doesn't show up as a parameter for sending the email. And so that is a use of the sort of the explicit setting of one task as having a dependency on another. So this is really straightforward. It's pretty easy to write this down. You can get a lot more complicated with all of the features that Prefect adds. So I do want to take a few minutes to talk about things like scheduling and state handlers that you can see here. But again, once you've registered this particular flow with Prefect, you end up with the really nice page that you see here with the flow registered and ready for you to use. So,
I can interject briefly for a question.
Yes.
It's not clear to me with these flows, are they kicking these jobs off in parallel where they're parallelizable, but then passing the data explicitly as Python variables? Like the results of the job, like Airflow, you tend to write to something and then read it back in for the next job, if I remember correctly. Whereas this, if you're passing variables in memory, results. Exactly.
Yes, that is correct. And that's one of the That's actually something that they discussed in that blog post that I mentioned on prefect.io. Treating data as a first-class citizen, I think, is the way that they put it. So I want to talk a bit more about the extra features that we could use to customize the flow. So scheduling is really nice and easy. I tend to use cron clocks or just cron notation, and so you can do that if you like. The definition for a schedule that I have set up here is all I need to add to my flow definition to have a to get this particular flow running on the schedule that I've defined. Again, there are a number of different ways to define a schedule. So if you're interested, take a look. State handlers, as I mentioned, are just little ways to handle or to respond to the changing state of a task or flow run. You can pass your state handler as a parameter to either a registered flow or a task, and then your flow or task will then pick up that state handler and use it if the flow or task run works out to have those particular changing states. The email handler that you saw me refer to earlier is one that I use in many of my jobs. So email handler will it's just a tiny bit of code that will send an email to me and my boss if a job fails. And this is all you have to do to define that handler. Again, you just pass it in as a parameter to your flow or your task if you want to use it. And so for this particular definition, there's more here under do some things. Essentially, it's send an email. But the email handler just responds, in this case, to a new state that is a failure. But you can do many, many more things with this than my very simple example. You can also fine-tune task settings. So there are lots of ways to do this. You can use timeouts, retries, you can add delays between retries. As an example of doing this, you can see that I've got my get Azure data task. I've given it the @task wrapper, and I have passed a bunch of parameters into the task wrapper to, again, fine tune those settings for this particular task. I've set a 2-minute timeout on the task. I've given it 3 retries and a delay between retries of 2 minutes. And it looks like I've missed a parenthesis, so apologies. Again, the built-in logging capabilities are really nice. As a very simple example, you can call a logger using the notation that I've got here, and then use your logger as you would any other logging tool. And we've already seen an example of the formatting for the logs in the user interface. And then parameterization is also a really nice feature that allows you to add required, non-required parameters with or without defaults. It's very, very easy to set these up. In fact, the last time I gave this talk, right before the talk, I was like, I'm gonna learn how to use parameters. And I did in about 30 minutes and set them up and got them running. So it was really nice to just be able to do this very quickly and not have to spend a bunch of time reading documentation. Really, all you need to do to use a parameter is call the parameter class, and then RC, my parameter here, is good to go, and you can use it throughout the flow. I'll show you in my, so this particular parameter I named read_container, and I'll show you in the particular flow where this shows up what that formatting looks like. So this is in this guy. So you can see read_container shows up here. And so I can parameterize this run by filling in the nulls here and hit the run button. So again, this was just like, it took me like less than half an hour to figure this out and get it up and running, which was very helpful as I had a talk to give. So pretty nice. Then let's see, what else do we have? Okay, advanced features, which I'm not going to go into a lot of detail with, but I'm going to give you a few ideas of some interesting advanced features, and there's a lot more out there that you can take a look at. So I've only been showing you a single type of task, which is a Python task, the most boring of all of the kinds. But there are lots of interesting tasks built in to Prefect or the Prefect API that will allow you to do some pretty cool things without too much setup, which is nice. So there are tasks for dealing with AWS, Databricks, interacting, that is, with these services, with Redis, and actually many others. There are quite a few services that are supported with lots of really nice specialized functionality. There is also a lot of interesting stuff going on with dynamic DAGs. So we have the ability to do task looping as well as task mapping. The mapping functionality looks, it's sort of a way to use MapReduce, which is pretty cool. And again, many more, I think, yes, many more interesting things that are in the works or already available to use. So that's the bulk of my talk. I did want to give you all an overview of the architecture that we're using, as well as our CI/CD integration. So a somewhat simplified view of our architecture is this. We have a virtual machine in Azure that has our Prefect, or production, that is, Prefect installation. Our on-prem GitLab server is dropping Prefect flows on the virtual machine. And then Prefect is using them to move data among all of these resources and many more, again, both local and cloud. There's a little more to this diagram. As I've mentioned, we have a dev server. I didn't want it to get too complicated. This is a good overview of what our setup looks like. And then one of my favorite things about this whole situation is the really nice CI/CD integration that we've set up, which has been so seamless. It's quite nice. So the way that this is set up is that a developer will make some changes in PyCharm or whatever their ID is and push those to GitLab. And then if that builds successfully in GitLab, GitLab will push the code to the virtual machine hosting Prefect, and will also at the same time register the flow with Prefect. So then Prefect living on that virtual machine picks it up, and the developer can go to the user interface and test and make sure everything's working and continue developing. And the process of pushing changes to testing the new flows in Prefect, generally, if everything builds correctly, it takes less than 30 seconds, which is so helpful. So that's something I've been really happy with. And that's it. That's all I have to say. So thank you all for hearing me out. And if you have any questions, I'd be happy to take them and probably not be able to answer them. So.
I had a quick question. So with the parameters, if you change them in the UI, does it record like the state that they were before anywhere?
So, okay. Do you mean like if you change them in the UI and then do a run, are those recorded in job information, or are you talking about like if you go back and want to do another run, will it have the original parameters?
Are they recorded somewhere what that run's parameters were?
I think I'm almost confident that they are. Why don't we poke around and see what we see here? Actually, I'm not sure that I have even run this. Oh no, it looks like I have. So let's see, let's look at a run for this particular guy. Peculiar shrimp, parameters, voila.
Awesome.
Yeah, so here they are.
Very useful.
It is very useful. Other questions?
Hey,
So
sorry.
I have a question. So when you use this prefect that I'm not quite familiar with, but what's the biggest difference, if you are familiar with Airflow, is the biggest difference you experienced that using these two platforms?
I think probably the API. They're fairly different. Similar enough that if you already know Airflow, it's pretty easy to use Prefect, but the Prefect API is, I think, probably the biggest difference. As a developer, that's the thing that you're going to be focusing on the most. But I think that like the differences are smaller things, such as like the way that you build an Airflow DAG versus the way that you build a flow in Prefect. The fact, as was mentioned earlier, that you can just pass data from one task straight to another in Prefect. There's no like writing out of data from between tasks. I think someone else had a question.
Yeah, thanks. Thanks for the talk. How do you and the team manage Python environments across, like when they're developing and then also in prod? Is there just one single environment, or do you have individual containers for each job?
Right now we have a single environment, which could change based on what we need to build out. That has not been an issue. I think largely because most of the jobs that we're writing right now have fairly similar setups and requirements. So yeah, right now it's one environment.
Okay, awesome. Thanks.
Very clear. Thank you for your talk. Do you have any thoughts when you look into this about how scalable, how robust it is when you're running a production environment?
I think it's pretty scalable. So as you've seen, like we're moving a fair amount of data back and forth, and we're doing totally fine with sort of the single server deploy. I think that if you really needed to scale this up, putting it on Dask would be awesome. And I haven't tried that. It's something that I hope to get to do at some point in the near future. My understanding is that it's also really nice and probably very, very scalable once you get Dask involved.
Mary Claire, I've got an interesting question. There are silos within the Duke and Duke Health organizations. Did you ever have to work with other schedules or other systems where you had to coordinate your jobs with other silos jobs that weren't necessarily written in Python using Prefect, for instance?
So you're absolutely correct. That is a very fair statement about Duke.
Experience.
Yes. Same after my 1.5 years at Duke. So for these particular jobs, let's see, I'm trying to think about, for these particular set of jobs, it has not been an issue. It's certainly something that could come up. We have had more cooperation among teams in the last, in the last pandemic than before times, which has been great. So I hope that it will be less of an issue moving forward. Fortunately, in recent memory, I have not had to sort of coordinate among different groups. I do not know what that would look like, honestly. So good question. Now I'll stay up at night worrying about that. Thank you, Sarah. Well, thank you all so much for having me. I enjoyed talking to you all, and thank you for your questions and your attention.
Thank you, Mary Claire. This is nice. All right, I don't have any volunteers yet for a lightning talk. Does anyone want to give a lightning talk? No lightning talks?
This is one of those rare meetings that I didn't think that I was going to be able to have any time to either prepare or deliver a lightning talk. I apologize for not having a lightning talk.
I think you have given enough lightning talks. You should be allowed to have a break sometimes. So. All right. Well, if really no one has a lightning talk, I guess that means this is the end of our program for today. Thank you everybody for coming out, and thanks very much to our speakers, Mary Claire and Eleanor, for your talks. They were very nice.
Thanks, Mary Claire. Thanks, Ellie.
Thank you all.
Thanks.
See you guys.
Bye, everybody.